So, yeah, today we'll talk about how to use isogenies for the purpose of, designing cryptosystems. So last week we described more like, the sort of a general theoretical background that you would need to do this. And I decided to structure the presentation chronologically. So what that means is, we'll go with, whoever came up with those ideas first, and then, all the way up to the latest NIST submission. And I'll try to identify some of the landmark contributions. All right, so as far as everybody knows, it started off with Jean-Marc Couvet in 1997. So what he did is he gave a presentation at the École Normale Supérieure in Paris about a submission to the Crypto 1997 conference, where he sort of laid out the foundation of how to use isogenies in cryptography, and then that paper got rejected. So I guess it was a bit ahead of its time, and then he forgot about it all the way up until 2006, when some other people started reinventing the same sort of ideas. Okay, and so then he felt, oh well, I guess I'll put it on the preprint. And then it went on the ePrint server. So if you go on ePrint and you ask for this, so the title of the paper is called Hard Homogeneous Spaces. And if you go on ePrint and you find that, it'll have a date of 2006, okay? But really, it was happening in 1997. So I'll describe first from a high-level perspective what that means. So at first glance, doesn't really relate directly to isogenies. It's about group actions, okay? So it technically, the group, and we'll see after that, how we instantiate, this group action using isogenies. But first, I have to notice that this general framework doesn't need isogeny. It needs a group that acts on a set and simply and transitively, okay? And the kind of hard problem that we hope that pertain to this action is, well, if I give you two elements of my set, should be hard to find the element G that acts on the first element to give you the second element. So he called that vectorization. And then there's another problem that he was hoping was hard, was that this when you see a parallelogram like with H1, H2, H3, it should be hard to find the H4 such that the same element acts on H1 to give you H2 or on H4 to give you H3. All right. So, and then of course there's other, there's other conditions. Typically, it speaks to the efficiency. Like you don't want your action to be hard to calculate, right? If I give you an element, but I didn't even list that because it's sort of common sense. But typically, if I give you a G, should be efficient to calculate the action of G, and that's not always the case, right? So, but in that case, it will matter for the efficiency of the crypto system. Now, the first sort of scheme, the first protocol that he described is about key exchange, all right? So now it's a kind of a Diffie-Hellman analog. Now, it's not, it has one more step, but I described it here the same way it appeared in the paper, right? But if you're familiar with Diffie-Hellman, that's essentially the same thing. So Alice chooses an element in the set and an element in the group, acts with the with the group element on the set element, and sends the two elements H0 and H1. And then Bob will choose a group element. So that's kind of like his secret ephemeral key, and acts also on H0, okay? And sends back H2. And at some point, and that's because, of course, the something I should have mentioned, but the group here is assumed to be commutative. Then on the one hand, Alice can calculate G1 acting on H2, Bob calculates G2 acting on H1, and that's the same thing, right? So you do because the multiplication commutes in G. So that allows them to create a shared key, and that really resembles the Diffie-Hellman key exchange protocol, where for those of you guys who know, and you know what I'm talking about. Otherwise, it's a protocol where Alice and Bob are exponentiating the same element with secret exponents, and at the end, what it is the element, the shared key is that element to the power raised to the power of those two secret exponents. Okay, and so here, of course, you see why that vectorization condition is important, because otherwise, if you listen to the communication between Alice and Bob, you'll get their secrets. If you were able to, given two set elements, find out which group element acted on the first one to give you the second one. All right. Now, so we also have an authentication / signature protocol. So, and that works also very similarly to a lot of other things, including proving discrete logs and those sorts of things. And basically, given two set elements, proving the knowledge that of a group element that acts on H0 to give you H1. Right, and so we've talked before in the seminar about zero knowledge proofs. So we repeat a round where a dishonest prover has a 50% chance of passing, and then it's repeated sufficiently many times in order to make it impossible for the dishonest prover to succeed. And so the way it works here, if you're the prover, you first generate a random element in G, okay? And you send what is called, so what's typically called in these kinds of protocol, your commitment. So you send G prime acting on H0, which is public, okay? And then the verifier will communicate a challenge to the prover, and the prover doesn't know the challenge in advance. And the challenge is, in this case, because it's the simplest way to proceed, is just one of two questions, okay? So it draws a bit, 0, 1, and depending on that bit, the prover will have to communicate a response to the verifier that's going to be different. So if the bit, in one case, the response needs to be just that random element that was acting on H0 at the beginning. But if the response is 0, then it's going to be that G prime times the inverse of your secret. Okay. Now what's important here is like G prime is distributed uniformly at random, so multiplying this to your secret is not going to reveal your secret. And then the verifier can check that the response time H0 is the commitment if the bit was 0, or if the bit was 1, it's the response time H1, which is equal to the commitment. And something that we've mentioned before is that, of course, if you knew the question in advance, you could adjust your commitment in order to pass all the time, right? Like the reason why this is difficult for the prover, the dishonest prover, to pass this with probably significantly better than 1/2 is because they don't know which question they're going to be asked. Okay. All right. So, and maybe, we've said that before, but what's important to know is that then you can turn such a protocol into a static proof of knowledge, and then that can be in turn transformed into a signature. Okay, with the Fiat-Shamir heuristics. Now, how does that relate to elliptic curves? So elliptic curves can be thought, we'll see what kind of groups and what kind of curves, but this framework can be thought of as a instantiation of this sort of a more generic framework of hard homogeneous spaces. So you assume that you have an ordinary curve, E0, and so the group of points given to you like by q+1 minus the trace. And we're going to build a group that acts on curves with those parameters via isogenies. Okay, so the group action, so there's going to be a group, and every time the group acts on curves, basically it's like applying an isogeny of a certain degree. So something that was mentioned by Wissam is that, so you have always the Frobenius endomorphism that's lying around in the endomorphism ring of your curve. And that endomorphism, it has, you can associate, so it can associate a minimal polynomial here, and that minimal polynomial is going to define a field. All right, so it's going to define a quadratic field. And so in that field, you can look at the endomorphism ring. So Z, so you're going to first look at Z adjoint the Frobenius. That's always in your endomorphism ring. And then sometimes your endomorphism ring has more. And what you know is that however much more it has, it's going to always be stuck in a ring that is called the maximal order of this field. Now, if you don't know what the maximal order is, just think of it as just some ring, and we know how to pinpoint that ring. You know, it doesn't go much higher than that. And so we know that there is a ring such that you know, like that is stuck in between those two rings, Z of pi and the maximal order of that quadratic number field defined by that equation that I just presented before. And so that ring has ideals, okay? So, and these are the ideals are the elements that are going to act on curves. Now, something that I believe was mentioned by Wissam is that you can construct isogenies from their kernel, okay? And so what we're going to do is basically we're going to define a kernel from an ideal. So, so if you have an ideal of your endomorphism ring, you can define a kernel, which is essentially, you know, all the points that are going to be, that are vanishing at the endomorphisms in that ideal, okay? And then from a kernel, you can create an isogeny, right? So what we're interested in here is have a group act on those curves. And so to make it fit with the framework of hard homogeneous spaces. But something that I think I've said, but if I did not, I'm sorry, that group also is finite. And right now, the group of ideals is not a finite group. All right, so that's a bit annoying. And since it gets a little technical, we have to sort of identify ideals whenever one is equal to the other one times a principal ideal. So principal ideals are those ideals that are all the multiples of one single element. And then when you identify two ideals this way, so you create sort of an equivalence relation between ideals, and then you quotient that group of ideals, you get a finite group. And that group's called the ideal class group of your ring. And that's the group that's going to act on curves, okay? Now you may wonder, like, are we losing information? And, you know, because, you know, I take two ideals that are completely different, and how comes they act exactly the same? Because these are not creating the same isogeny, but those isogenies are equal modulo an isomorphism, right? So then what you're looking at is, in fact, not action on curves, but actions on the isomorphism classes of curves. But that's really not a big deal, especially from a purely practical standpoint, because those isomorphism classes, they're identified by the J invariants of the curves, right? So you can think of acting on a J invariant, right? And those J invariants, they're really easy to write down. So the moral of the story is the following. We have a group of classes of ideals of a certain ring, and that group acts as isogenies on classes of curves. And then, so every time you have an ideal, the sort of resulting isogeny that you create that way has a degree that is equal to the norm of the algebraic norm of the ideals, or equivalently the size of the kernel that you create. So this is all the same thing. The degree of the map that you create, the size of its kernel, or the norm, the algebraic norm of the ideal that you're using. And of course, one of the issues that I mentioned, I didn't even write, but I mentioned I should have probably written down that we want the action to be efficient to calculate. And I said, well, you know, sometimes it is and sometimes it's not. In particular here, if I give you an ideal of very large norm, it will correspond to an isogeny of very large degree. But first, it will create a very large kernel, and then it's going to be really inefficient to calculate the isogeny that it corresponds to. So there is a workaround. It involves some calculations, and we're going to pause here, but I'm going to mention it, and then because I'm doing things chronologically, that this was not really solved at the time, but basically you want to decompose your ideal as a product of small things, okay? Because essentially your ideal is going to be hard, the action of your ideal is going to be hard to evaluate when the norm is large. But if you have it, you know, expressed as a product of small things, then each individual element in your product, its action is going to be easy to be calculated. It's going to be easy to calculate, right? So the problem, of course, is easier said than done. So this thing here that consists in taking an ideal and then decomposing as a product of small, quote unquote, prime ideals, that's not easy, okay? But if you can do that, then your action is a lot easier to evaluate. So I say more on that later because, well, at the time, you know, these issues on the efficiency of those kinds of crypto systems, they were absolutely not solved, right? So like those calculations were like horrendous, and it was more of a sort of theoretical idea, but it really wasn't practical at all. And like I said, that idea was rediscovered in 2006, which is what prompted Jean-Marc Couvain to put up a preprint on the ePrint, right? So this was published by essentially Stobunov. It's on his PhD thesis. But again, same idea and same drawbacks, which means it was really inefficient and nobody really thought of using isogenies that way. And in parallel, there were people who decided to create hash functions from isogeny graphs. And that was also 2006. But so the ideas here are completely different. They're not trying to do key exchange. They're not trying to do a zero-knowledge proof of an isogeny. Instead, what they want to do is a hash function. So in case you're not familiar with that notion, what is a hash function? So a hash function takes as input a sequence of bits that is arbitrarily long, and I will return what they call a digest, which is going to be a sequence of bits of finite length, typically between 256 and 512, okay? What's important, of course, compared to other cryptographic primitives that you might be used to, like encryption, signatures, MACs, this doesn't require a key, okay? So, you know, sometimes when you think, oh, what do we want for an encryption scheme? And we say, well, it's got to be hard to decrypt if you don't have the key. But here, nobody has a key, right? So a hash function, everybody can evaluate it. So what we want, as far as its properties for cryptographic use, what we want is that it be hard to invert. Maybe we should close that, yeah. Thanks. So what we want is, we want it to be hard to invert. We want it to be hard to also invert in two different ways. And one big sort of, one that a lot of people mention is collision resistance, right? So typically, people, when they say, okay, is this hash function secure? They'll typically think, well, is it difficult to find two elements that are different but somehow hash to the same digest, okay? So that's what we're going to talk about, collision resistance. But first, how do we construct an isogeny from supersingular curves? So one thing that I would like to mention also, and then you'll hear, you know, I mean, sometimes people like to, yeah?
I want to make sure I understand on the collision thing.
Yeah?
So the domain of that H is really much bigger, right? The x's are much longer than the H axis in bits.
The H x's?
Yeah, that's yeah. AX.
But then how is that hard?
How is what hard? To find a collision?
Yes, so that function h has a very much bigger domain than a codomain.
Yeah, so there are, no, so just to be clear, there are plenty of collisions, they're just hard to find. Meaning,
But
if you're willing to pay
bigger,
2 to the 128, you'll find collisions. The postulate here is nobody wants to pay 2 to the 128. All right? So back to the, one thing that I want to mention also, like that sometimes get people upset. So this is not the first time isogenies were used, right? Because there was always Couvain's contribution, but it's the first time supersingular isogenies were used, okay? So some people think it's important. So supersingular, so the supersingular isogeny graph is what we're going to use in order to build this hash function. So the nodes are elliptic curves that are supersingular, right? And so first off, so for supersingular curves, you don't have to worry too much about the field definition. They're all defined over fp squared. So P really identifies that. And then L is the degree of the isogenies that we're going to be considering. So typically, L equals 2 is a perfectly valid choice. Okay. And what do we have? Well, what does this graph look like? So first of all, like just in case I wasn't clear, my nodes are the E's, the curves, and then you go from one curve to the other if there is an L isogeny, so an isogeny of degree L between those two curves. All right. So what does it look like? So you have about P over 12 vertices in this graph, so it grows linearly with P. So P here, they're astronomical. Typically, they have hundreds of bits, right? So the P is extremely large, but L is going to be very small. So L typically 2 is okay. So it's L plus 1 regular. So what does that mean? It's just like every time you start from a vertex, you have L plus 1 different ways of coming out via an L isogeny. It's connected. And also, it's got good expansion properties. I believe Wissam mentioned that. And that's really important because you really want that there be rapid mixing properties in that kind of graph. And I will see why regarding the properties of a hash function. Okay? Now, how do you want to hash? So I'm going to restrict now to the case L equals 2, but it can generalize to whatever prime L you decide to choose. So if it's L equals 2, the degree of the isogenies you're considering, then your graph is 3 regular. So if you arrive, you're going to navigate the graph. If you arrive to a node, then, if you don't allow backtracking, so if you don't allow yourself to turn around and go back to the node that you came from, then you'll have essentially 2 possible directions. Right? And what you're going to do is you're going to move in that graph bit by bit. Right? You're trying to evaluate a hash function that's coming to you described by bits, zeros and ones. And then when you have a 0, you're going to choose one particular direction in the isogeny graph. And when you get a 1, you choose another direction. Okay. So, and of course, there needs to be sort of a canonical way to choose those directions. So they solved that in their paper, but otherwise you would be out of luck because two people evaluating the hash function need to be choosing the exact same directions when they see zeros and ones. Okay, so there is a canonical way to do this. And at the end, everybody decides on a common starting curve, and then you follow this procedure. And when you wind up at the end, you can declare that to be the hash. Okay. So what does it mean to be collision resistant for this hash function? Right. So collision resistance in this case means, so remember, collision resistance is I don't want x different than y and h of x equals h of y. So in this case, it means that starting from a given curve, I don't want that there be 2 different paths to get to the curve that corresponds to the hash. All right. So what does that mean that you found 2 different curves? Essentially, you have a cycle in the isogeny graph, right? So you don't want people to be able to find, easily those cycles. Okay? Now, the cycle could also be viewed as an endomorphism of the curve, right? So if you look at the composition of all, so this is all L isogenies, right? I mean, for example, L equals 2. So isogenies of degree 2 that you've composed all the way here. And then you can go in that direction by taking the dual isogenies of, so a sequence of the dual isogenies that from that sequence of isogenies that go from here to here. So you construct an endomorphism, all right? So finding endomorphisms in the curve is pretty much the same thing as finding collisions on your hash function or finding cycles in the isogeny graph. So the goal here for collision resistance is that it be hard to find cycles, right? So that's typically an assumption, but there's something interesting that they came up with, and then there's a lot of research on how to analyze the properties of this isogeny graph. There is a way that you can work on the parameters in order to actually rule out the existence of certain cycles of a certain length. So it's even better than to assume that they're hard to find, as if you can argue they don't even exist in the first place, right? So, for example, if you want to avoid cycles of length 2 to the n, all right, so you remember that endomorphism ring, in the case of a supersingular curve, is isomorphic. Oops, that's actually not true. It's an order in a quaternion algebra. Oops, my bad. And so the degree is the norm of that element. So my element, which is an endomorphism, it corresponds to an element in an order in a certain quaternion algebra, and its degree is a norm. So here I want to give some arguments. So if I choose my parameters carefully, I could say there is no cycle of, say, length 2 to the n. So if you look at the minimal polynomial of your element, you will have this form here. And if you assume that the endomorphism you're looking at, is not just a composition of, say, a multiplication by L to the n, so something that corresponds to an element that is essentially rational, then that minimal polynomial will have to be reducible, and then defines a quadratic extension, right? So defines a quadratic number field. And then P is ramified or inert in there. And so you can look at all the potential polynomials that you may generate with hypothetical cycles, so hypothetical endomorphisms, and look at the conditions on P that it gives you in these fields, and then choose P in a way that it will never satisfy this condition, right? So the condition in particular is it needs to be ramified or inert in those fields. And those conditions, well, you can essentially rule them out by making the prime split in the fields that could be potential minimal polynomials for those endomorphisms. So if you take, for example, so this is only practical for small cycles. So for example, like let's say I want to rule cycles of order 2. So this is what the polynomial might look like. And then it's going to be reducible only if the trace is among this sort of short list of possible numbers. And I can look at all the fields that are being defined by all these potential polynomials and make sure that P splits in all these fields, right? And this translates into congruence relations on P. I mean, congruence conditions on P, right? And so if P satisfies, well, in this case, 4 different congruence conditions, then you're going to say, okay, I know for a fact that if I choose this P, I will never have 2 cycles in my endomorphism, in my isogeny graph. And that's pretty cool. But bearing in mind, of course, that this is practical only for small cycles. And in the end, what we really care about is not so much to argue that there is no cycles, because there are going to be anyway at some point. But really, the hardness assumption is that it's hard to find. Okay? All right, so now we fast forward to 2011, when I saw supersingular elliptic curves were used, this time to do the same sort of analog of Diffie-Hellman that we were talking about at the beginning. So when we had a group action, it was kind of easy, you know, act with one element and then act with the second one, and it's the same as, you know, acting in one direction. I mean, acting with the second one first and then after, right? So you can sort of interchange the order in which you act. Okay, but if you were to use supersingular, isogenies on supersingular curves, it's not so clear at the beginning how you would create sort of this commutative diagram. And that's what David Zhao and Luca De Feo solved. So this time, no group, all right? But they're going to just try to find a kind of diagram that Alice and Bob can sort of construct independently, where they end up on the same curve so that they exchange a secret. So how are they going to proceed? So remember that a kernel of order n corresponds to an isogeny of degree n via the Velues formulas. And then the torsion, so the n torsion has this shape, okay? So what Alice and Bob want to do, so the sort of game they want to play is that they want to each select a kernel within the, you know, so if they have NA is a number that is co-prime to NB, so Alice will choose an element of order NA, and Bob is going to choose an element of order NB, and that gives them both sort of like secret kernels. And in those two kernels, they can define isogenies that are pointing in different directions in the isogeny graph. And the goal would be, if they could get, you know, the isogeny that corresponds to the kernel that's, you know, the sort of the composition, I mean, you know, the group that is generated by both of these elements, okay? But there's a little trick here because, well, they can't really exchange the kernel that they choose, you know, these are elements that they can't really give to the other party, right? So since we have this shape of the n torsion, right, I have two generators, so this everybody knows, and the real secret values are going to be the coefficients of those secret element alpha A and alpha B, right, with respect to this basis. So, you know, Alice is going to have those two numbers, mod n A, and then Bob is going to have those two numbers, okay? And somehow they need to play a game where at the end, so they navigate this isogeny graph, and in the end, they want to converge towards the same curve, or at least the two curves that are isomorphic. Okay? So I figured I'm going to do the diagram live, and what could go wrong? We'll see. So let's say you start with a curve E0, right? And so if you're Alice, you can go from E0 to, say, curve E sub A, all right? So Alice has that curve, and then that's, you know, by quotienting by alpha A. So she uses, nope, sorry, I already messed it up. So EA, which is E0 quotient by the thing that I just showed, right? So EA is E0 quotient by, right, alpha A. And then Bob can go to a curve EB, okay? And he does the exact same thing, but he can quotient by his own secret subgroup. And then, ideally, right, they want to take their kernel information and then move the way, you know, move to sort of converge towards the same thing. Problem is, well, you know, that's not going to work because the basis of the torsion that they have on E0 doesn't really correspond unless when Alice calculates EA and tells Bob that she landed in the curve EA, she also kindly, I realized I didn't choose, so I'll say phi A is Alice's, I'll call that phi A. Oops. I'll say this is phi A, and then so she gives not only the curve, but also the image of the NB torsion. So like, oops, I knew this was going to be a bad idea. So phi of QB. So you see what's happening here in phi A. So Alice has a secret isogeny that she calculated, and she's going to push the NB torsion through this isogeny to give Bob not only the curve EA, but also the image under her secret isogeny of the NB torsion, which Bob needs in order to create his kernel from the linear coefficients that he has from PB and QB, okay? And at this point, you're probably wondering, is this a good idea to give out some extra information right here, you know, on this isogeny, right? Because at first I'll just give you the curve. If we give you just two curves, it's just the problem of finding an isogeny. If you believe it's a hard problem, you shouldn't have a issue with, you know, being given two curves and linked by secret isogeny. But here you're being given two curves and the image of certain select points by, you know, the secret isogeny. Right, and so for the longest time, nobody knew how to figure out a way to use that. And then Bob will calculate EAB, and that's going to be EA. So he takes Alice's curve and then quotients by essentially so MB. Applied to you know, phi A of PB. So he takes the So he takes the images of the torsion points, and then gives the exact same linear combination that he had chosen at the beginning, right? So that's PB plus plus NB. And then phi A of QB. All right. And then Alice, and I'm not going to write it down, but Alice does the exact same thing, except so this time it's Bob that publishes the curve EB that he calculated, plus the image of the basis of the NA torsion, so that Alice can go that direction. And then they sort of meet in that common curve, I mean isomorphism class of curves. So, so what happened with this thing? So it was published in 2011, and then in 2017 there was this standardization process by the NIST, where they standardized KEM, so key encapsulation mechanisms, and digital signatures. So they submitted a proposal for a KEM. All right, so, and it was called Psych, supersingular isogeny key exchange, I suppose. So it's a bit, so this is a key exchange. A KEM is a little bit different, but essentially the same thing. So I'm not going to go into the details of what's the difference between key exchange and key encapsulation mechanism. That diagram is there, right? So this is really the key ingredient is creating this commutative diagram where Alice and Bob wind up having the same thing in the end. And then it made it all the way to round 4 of the selection process. So it took years, and right, for about 10 years, nobody knew what to do with those torsion points. I mean, the image of these torsion points that you have here. And then 2022, like people finally found that. And it was actually using math that had been around since maybe 20 years before, right? So like the math was always there. It just took 10 years to the community to finally find that, yes, you could use it in order to crack SIDH/psych. So at this point it was a bit of a low point for isogeny-based crypto, because once this was broken, then everybody was like, well, you know, I guess there's no point in using isogenies for cryptography. I mean, some people like shortcuts, right? So it's not quite true, but you got to use different ideas. In particular, you can't really, when you look at the isogeny problem, you know, you really should analyze what's going on, and if every time you see, like, if there's like this little tweak of like adding extra information, that's usually not a good idea, right? So going back to group action then, in 2018, So that's sort of like in parallel to the NIST standardization process. There's a group of people who said, well, this group action thing would probably, it may not have been that bad. You just need to find the right setup to make it efficient. Okay, so previously I said it was a bit hard to make it efficient, but they revisited the idea. Oh, by the way, so they call it CSIDH, right? So the C is for commutative. It's pronounced seaside. And there is a story of they were by the sea when they came out at a conference that was by the sea when they came up with the idea. And so here you redo hard homogeneous spaces, the hard homogeneous spaces sort of framework of Couvain, but this time using supersingular curves over FP. And sort of from a high level standpoint, the general idea is if you're looking at a supersingular curve defined over FP, you'll have a better luck at finding primes for which the kernel that you calculate in order to calculate their action is only made of rational points. Because when things are not rational, you have to go get the information in extension fields of degree that can be really high and that really make everything inefficient. So when you have when you're trying to calculate actions of small primes, you're also hoping that those primes they generate rational kernels. And so so essentially what that means is in this case you want the cardinality of the curve to be zero mod about the L's that you're going to be using in order to act on the curves. Okay, so you're going to use prime ideals that are above some rational primes. Okay, and in this case, so you're going to restrict to oops, I don't have my marker anymore. Oops, yeah, so you're going to restrict here to the ring of FP endomorphisms. So remember the ring of endomorphisms in the supersingular curve, it's this bizarre object that lives in quaternion algebras, and nobody wants to work with that. But if you're looking at FP endomorphisms, these ones, they are smaller, right? Those rings are smaller and they're quadratic orders. So they're rings of dimension 2. I mean, they're orders of rank 2. And the ring of FP endomorphisms, it could be just one of two things, okay? And so once you know that, right, you're looking at this ring, and then you're going to try to find sort of a small set of, I mean, small, you're hoping it's as large as possible. So a bunch of primes of small norm that divide P plus 1. And that's, if they do that, so their norm divides P plus 1. If that happens, then it's going to be easy to calculate the action of those prime ideals. And remember what I said before, typically if I give you a very large ideal, and by that I mean an ideal of very large norm, it's going to be hard to evaluate directly, but if somehow you can break it down into a product of small prime ideals, and if those prime ideals individually are chosen so that, you know, the action of those prime ideals is easy to calculate each individually, then you're going to have an easy time evaluating the action of an ideal despite the ideal having a very large norm. So we talked about the group that's acting. It's still the group of fraction ideals. I mean the class group of the order. And I said at some point, I said, well, I'm going to say a little bit more on the action of decomposing an ideal later. And the reason is, it's actually not a trivial problem, right? So what they did is they managed to, I mean, they set up the stage for having a sort of large number of small primes whose action we can efficiently compute, and that's great. But that doesn't mean we know how to break down each input ideal as a product of those primes. You may think, oh wait, but isn't it just prime ideal decomposition? It's not, because remember we quotiented by this equivalence relation where we identify two ideals when they're equal mod a principal factor. And what that means is, if I give you an ideal of very large norm, all right, it's going to be in the same class as a product of a short set of ideals. But those ideals don't divide necessarily the ideal that I gave you as input. All right, so it's not just a question of dividing by p and seeing what exponent I get. Right, so it's something a little more subtle. And so the way we calculate the ideal class group usually is if we have a set of ideals that generate your class group, then you can consider this surjective morphism where you take exponents and you map them to the product of those generators raised to the exponents. And then if you indeed have a generating set, then this thing is, this map's going to be surjective and you're going to have this identity here. So finding the class group is essentially the same as finding vectors like this of exponents of relations of the form the product of your generators raised to those exponents is the neutral element of your group. All right. And now here's the thing. If you're capable of finding whatever decomposition of your input ideal, and then those guys could be really large. That's really the issue here. So you don't want that to be large because when you evaluate the action of, say, p to the raised to an astronomical power, you have to do this in sequence. There's no such thing as square and multiply strategy here. You have a big power, then you're going to pay the price of evaluating exactly the number of times that's in the power. But you can find a better decomposition if you find, well, any decomposition, basically, any set of coefficients that's in the same coset mod the lattice of relations between your generators, that's also going to be another valid decomposition. So to find a small one, what you want is find one that is close to this input vector, so the original decomposition you had, modulo the lattice of vectors that create relations between your generators. And the real problem, it's here, right? With this idea is, well, it requires you to calculate the class group, and the class group is hard to calculate. The best methods that we have, they're essentially the same, based on the same ideas as integer factorization. All right, so, and you probably know that the hardness of factoring integers, this is the sort of the core hardness assumption for RSA. Okay, so we hope, in fact, integers are hard to factor, and that means that sort of, well, because we're using with the best we know to calculate the class group, essentially using the same methods, then we're also hoping, in fact, that calculating class groups are hard. So they did it for 512-bit P, which is already pretty heroic, and nobody knows how to do better. Okay, so then you're sort of stuck by this pre-calculation that you need. So now you need to do this once, and every user of that crypto system could benefit from that, right? Like that could be made public, and everybody could use this lattice of relation and this recipe to make your decompositions of input ideals better. But the problem is, even the one-time pre-calculation might be just out of range for everybody. Now, there's been, and I'm not going to say much about that, but there is sort of like a way to generalize this whole approach, and it's what people call the orientation of supersingular curves. And the idea is to find embeddings of quadratic orders into the endomorphism rings of supersingular curves, and this time not necessarily defined over FP. Okay, so here what we had was we were mapping the generator of our what was I going to say? The generator of our order mapped to the Frobenius. Now, why is it potentially more interesting to have a more sort of broader variety of orders that could be mapped into the endomorphism ring? Is because, well, this group action then could be that of the class group of, say, an order that is strategically positioned as a suborder of a maximal order that has a much smaller discriminant. So the long story short is that when you're in this sort of case where you have a suborder of a very small maximal order, then calculations that are easy then translate into the suborder that has like a very massive discriminant, and that would be normally, with the sort of factoring-like methods, be hard to compute. So the long story short is like there are ways to generalize this approach of group action to supersingular curves in ways where we control the order that we use, and then sometimes we can find some tricks where we can calculate, the class group and the compositions of ideals better. But we're still struggling with efficiency, because then the embedding itself is something that is not always easy to calculate. All right, so now to finish, I want to mention the newest NIST submission about supersingular curves, and it's called SKISign, for short quaternion and isogeny signature. So what happened was in 2023, well, first this was published in 2020, but then in 2023, NIST accepted new submissions for what they call the on-ramp selection process for digital signatures that are post-quantum, okay? So they accepted a bunch of submissions, and then the people who were, well, I mean, I guess a lot of the people who were involved previously with the Psych submission, the one that got broken, they figured, well, actually there is a way to provide digital signatures that's actually quite competitive. Okay? So, and the way this works is it's again a proof of knowledge. Okay? So it's again the same sort of like a strategy of saying we're going to derive a signature from a proof of knowledge of a certain witness of a relation. And here the witness is an endomorphism in the endomorphism ring. And so it's been proved in parallel to that finding endomorphisms, finding all of the endomorphisms, or finding isogenies, they're sort of like in the same, is of comparable hardness. And the way the protocol works is, so you have E0 that is fixed. The prover has a secret isogeny tau and publishes EA, okay? Then the prover commits to a curve, okay? So the prover will draw an isogeny psi, and they commit to this curve E1, okay? And so they show that to the verifier, and the verifier is going to say, okay, now I give you a challenge, which is I draw an isogeny phi at random, and I publish this curve here. And then the response of the prover is to give this isogeny. Okay? And so, okay, so, and then if they can't, I mean, so it's a one round thing this time. Remember when I said previously the soundness error, like you can expect an adversary to flip a coin to guess the question. Here there's no guessing the question, because there are lots of possibilities for this. It's not the question is not a 0 or 1. It's like basically there's so many possibilities. Only one round suffices to assess that the prover is most likely honest. Okay, and I'll say just a few words about what really needs to be done to prove that this thing works. So first of all, when they provide, there's a subtlety here, and I'm not going to get into the details, but when they provide this isogeny, they don't do it by just taking the this path here, okay? Because otherwise, the kind of endomorphism that you're really proving you have is just something trivial that everybody does have. So instead, they're using techniques where if you know the endomorphism ring on both sides, you know how to produce isogenies that are, of power, a degree of power of a prime. And it's sort of independent from that path. So they really produce a path that is computationally hard to distinguish from other paths, okay? And the special, what's called the special soundness, and it's really something I'm not going to get into, like I'm just going to wave my hands here. When you prove security of a zero knowledge protocol, one thing you're going to say is, if you have two accepting transcripts, are you able to retrieve a witness. So that means essentially, morally speaking, it says if you can prove, then you should have the power, you should really have the witness. That's really what it means. And in this case, what that means is like if you find essentially two different paths, you can compose those paths, right? You know, going one direction and then the other direction, and then you create an endomorphism, a little bit like when we were talking about those cycles in the hash function thing, you know, when we had the graph, and I said if you had two ways to travel, you know, from A to B in that graph, that gives you a cycle, then here this is exactly the same thing. So it proves that if you can answer two questions, then you should in fact have the witness. And then zero knowledge is another property, and I'm not, again, waving my hands here, but like this really should be independent, or at least computationally hard to distinguish from something that comes from this path here, okay? So this is really like, I'm just powering through it, like, because it's the end of the talk. I'll just mention one last time is the kind of, and it's perhaps, you know, if there's one takeaway, you know, from a talk on isogeny-based crypto, is that the kind of schemes that are being produced, you know, using those assumptions and then you know, deriving chems or digital signatures, is that they're usually very compact. So you see the public keys are 65 bytes, NIST level 1, and the signatures are about 150 bytes, okay? And this is like by far the smallest among all the competitors for this digital signature competition, the standardization process. It's really by far the most compact option. And usually the drawback of isogeny-based crypto schemes is that they're a bit slow, right? So they're hands down the most compact schemes, but they have to really work hard to find tricks to make those calculations use less CPU power. All right. Well, thank you for your attention. And then if you have any question, then I'll answer them.